general relativity, step by step. I've been considering gravitational waves, and I've been considering the two polarizations, which I've called plus for this one here and cross for this one, A plus and A cross for the strengths. And I've got these rather thumbnaily, rather amateurish drawings here of what they look like. Now that we've got that, what I want to do is to show you a little bit more of a slightly more careful calculation with a more numerically accurate picture. And I've got my R programming language here, which I use for this sort of thing. And if I source my if I source this little pre-prepared thing I've got, which I can open, I've got this little function called GW. And I'll just spend a few minutes talking about this. I don't want it to be a programming course at all, but the basic gist of it is that we've got a little function here, and the default is a 3% strain in the plus polarization and 0 in the cross direction. But of course I can change these, and I'll show you that. We've got some other arguments here which I'll talk about later. The operative lines are these ones here. There's the cross perturbation to the flat space situation, and the cross perturbation and the plus perturbation here. And this is the important line here. It's e to the power I times the time, e to the it. So that's the oscillating component there. And the thing that's actually plotted is this one here, which is the background position, the Cartesian position, plus the real component of these complex perturbations here. And we'll see why that's important later. So the first thing I'm going to do is show you a gravitational wave with zero strength, and it sets this beautiful system up here. I'm going to try and resize the window here. Just a minute. It doesn't like it. Sorry, that was a bit more faffing around than I expected. I had to pause the recording there for a few minutes. And what we see is a whole bunch of particles represented by little circles in the XY plane, and they're all in free fall, and nothing unusual is happening because these guys are just sitting in flat space. Now what I'm going to do is change, I'm going to say plus equals 0 and the cross polarization equals 0.03, let's just say. So let's see what that looks like. So now we're going to have a non-trivial gravitational wave. And lo and behold, these particles are oscillating. We can see the cross pattern here and here. You can see that this line here is, I guess, the line of eigenvectors. We've got two, we've got one there and a cross shape. It's a cross polarization. Have I got it the right way around? Yes, it's setting a cross perturbation. And we can see that as you get further and further away from the origin, the oscillations are getting larger and larger in amplitude. It's important to remember that each one of these particles is at rest. You could put a fish tank in here and it wouldn't slosh about. You could build an elevator around one of these. In fact, I might have even I should have drawn a little elevator around this thing, and you would not know that anything odd is going on if you were in a little box and couldn't look outside. Your fish tank would not slosh about. And yet we've got this peculiar oscillation here. Let me just stop that one. I think I can stop it thus. And I'll show you the plus polarization. Plus equals 0.03, and we'll set the cross to 0 and have a look at that. Yeah, that should work. There we go. And it's the same picture, but about a different oscillation. You can see how the eigenvectors are in this direction and this direction here, about the center. And we can see that the oscillations are getting more and more higher and higher amplitude as you get further away from the center there. So that's quite nice. Let's stop that. No, I'll just let that go for a little bit longer and watch it. Each one of them is at rest. Each one of them is at rest. Each one is a local inertial frame. There you go. Let's stop that. And now we can do something. We can add both of these together. We can have two polarizations here, 0.03 and 0.03. Let's have a look at that. And we see something a little bit more well, it's just a linear superposition of those two things. They're just oscillating in a slightly different direction. There we go. So it's that's what it looks like. Now then, what I'm going to do now is put a complex value for my cross polarization, and this will affect the phase. And so now, instead of being in phase, these guys are out of phase. The plus and the cross polarization are out of phase. Let's have a look at that. Aha! Now what's happening is each one is going round and round in circles. You see, it's got a wiggle on it. Each one's going round in a circle. Again, this point here is at rest in the middle. They're all at rest. All of them are at rest. But nevertheless, the proper distances between these particles is changing. They're at rest, but the proper distance between them is changing because the space between them is not flat. Well, it's because it's got a gravitational wave passing through it. There it is. Isn't that nice? Let me stop that. We'll do it the other way. We'll have a polarization. We'll have a negative number there. And it goes the other way, of course. Isn't that great? So this is why you use the real part of e to the power I times t, because you can just adjust your phases using the different using complex numbers, which is quite nice. Let me go back. I'll stop this. Let me go back to the initial case. I'll do the pluses 0.03. Where are we? Oh, let's do this one. Here we go. It looks like this point is special. It looks like this point is staying still and all the other guys are oscillating around it. So it looks like I've privileged this particular point here. It looks like that point's special, but it's not. And it's not special on physical grounds because contrary to appearances, all of these particles are at rest. If you put a fish tank at all of these positions here, that fish tank would not slosh about. If you were in an elevator, you would not be pressed against one of the walls. You would not have any perception of being shaken about. Yeah. So it looks as if this point here is special. However, let me just remind you of something which you probably know already, but I'll tell you anyway. Let me pinch in a little bit. If this is your galaxy here, what does a galaxy look like? It looks kind of like that. Then I'm sure you know that the other galaxies appear to be receding away from us. So the other galaxies appear to be moving away from us. And so it looks like where the centre... I'm not drawing this very well. That's us here. And it looks... Oh, what am I trying to say? All the other galaxies are receding away from us. There we are, that's us in the middle. And all the other galaxies, I'm not drawing this very well at all. All the other galaxies are receding away. So it looks like we're the centre of the universe, but we're not, of course, because if we were standing here, everybody would be moving away from us. And we've got a broadly similar view. Well, it's a very similar picture here. We've got this picture here. If I was standing here, then I would see the same picture. It would look just the same to me because, of course, the fish tank here is stationary. And I can show you that. I can stop this simulation here and I can set the centre equals, let's say, 0.8, 0.8. There we go. So now everything is around about this point here. It's the same physical situation. I've just used a slightly different way of plotting it, and I'm putting this point here not moving in my system. And so we can see that the physics is exactly the same, it's just that we're plotting it in a slightly different way. Yeah. Yeah, I wonder if I can change both of them at the same time. I wonder if it's robust enough. Oh, well, let's try it. Plus equals 0.03i, let's say. There we go. What does that look like? Beautiful. Of course, all of this is monochromatic waves. I've just got one particular frequency, but because it's linear, I can superpose different frequency gravitational waves, and I could have this one and another one at twice the frequency and another even higher frequency. So I've made a whole bunch of simplifications here. We're just considering one particular frequency. We've got two polarizations to play with, and we've got the phase and the relative phase, I guess, of the gravitational waves. But we're just considering monochromatic waves here. But I could have added waves of different frequencies to this. It would just be like It would just be like light, electromagnetic radiation, and we're considering different color light, different frequency electromagnetic radiation. And because the equations are linear, we have the principle of superposition, and so we can superimpose as many different frequencies at whatever amplitudes we like. Yeah. Stop.